Welcome to CivilizationX. Shade is not a cooling system. When humid air blocks sweat evaporation, indoor heat can still push the body toward failure. At 10:30 p.m., in a top-floor apartment, the wall beside the bed can still be releasing the day's heat. The anomaly is brutal. The most dangerous hours of a heat wave may arrive after sunset, indoors, when the body loses its recovery window. A 78-year-old woman sits on the edge of her bed, dizzy, collar damp, windows shut, door locked, convinced the danger is outside. But roughly 489,000 heat-related deaths occurred globally each year between 2000 and 2019. Europe accounted for 36% of them, more than 175,000 lives annually. In 2003 alone, Europe lost an estimated 70,000 people to heat. Researchers in physiology, climate science, and machine learning are now treating indoor heat as a forecastable system. Their tools combine wet bulb physics, building thermal models, localized weather prediction, and AI systems already able to predict heat waves 4 to 7 weeks before summer, while related forecasting models can predict river floods up to 7 days ahead and anticipate wildfire spread. The key question is not whether heat is uncomfortable. It is whether a room will cross the point where the body can no longer export its own waste heat. And if that point can be predicted, apartment by apartment, cities can intervene before a quiet bedroom becomes a medical emergency. The body is a heat engine. Metabolism produces heat constantly. Blood carries that heat to the skin. Sweat is the exhaust system. But sweat cools only if it evaporates. If the air is already loaded with water vapor, evaporation slows, then fails. Core temperature rises. The heart works harder to move blood outward. The brain, kidneys, and lungs begin to take the hit. Scientists use wet bulb temperature to capture this limit. At 35 degrees Celsius, wet bulb, or 95 Fahrenheit, at 100% humidity, even in shade, with water, a human body cannot survive for more than about 6 hours. But here's where it gets counterintuitive. Older adults and people with chronic illness can be pushed into danger well before that theoretical line. Jennifer Vanos, at Arizona State University, warns that the 35-degree number oversimplifies what happens physiologically, because age and vulnerability factors matter. Daniel Horton at Northwestern puts the next piece clearly: warmer nights limit the body's ability to recover from daytime extremes. That is why the safe night sometimes never arrives. Buildings make this worse. Roofs and walls absorb solar energy all day. Then it's slowly after dark. Older top-floor apartments, poor insulation, weak ventilation, and trapped humidity turn the room itself into a radiator. So, the deadliest period may not be noon on the sidewalk. It may be midnight in bed, in the shade, with water nearby, while indoor heat and humidity keep the body from cooling. The trend line is already moving the wrong way. In the United States, heat-related mortality rose 63% between 1999 and 2023, with a 117% acceleration in the last 7 years of that period. The obvious defense is air conditioning. It saves lives immediately. But solving that created an entirely different problem. Building cooling already uses almost 10% of global electricity, and cooling demand is projected to rise 210% by 2050 versus 2024. That can triple associated greenhouse gas emissions if grids stay dirty. During heat waves, peak demand also strains the same grid people depend on to survive. Low-income renters, elderly people living alone, and households on unreliable grids face the highest medical risk and the least control over the building or the power bill. So no, the answer is not simply drink water or buy more AC. Air conditioning reduces immediate risk, but it can fail during outages and deepen the emissions loop. The engineering answer is layered. Forecast dangerous nights early, prioritize vulnerable homes, and cut the heat load before it enters the room. Out of 100 apartments flagged before a heat event, many may be only uncomfortable, and a smaller number truly life-threatening. The challenge is not perfect prediction. It is acting early enough, without overwhelming emergency teams, or missing the quiet apartments where deaths actually occur. That is where AI becomes useful as infrastructure, not branding. Smart grid management could cut global power sector emissions by up to 2 gigatons of CO2 by 2050, while making grids more resilient under extreme weather. AI-powered thermostats can optimize energy use by up to 47%. Passive cooling materials, including smart paints, glass, gels, and coatings, can reflect up to 97% of solar energy and cut surface temperatures by up to 7 degrees Celsius. Etienne Voss at IBM says the critical task is alerting those most vulnerable before the heat peaks. The room that feels sealed and safe can still become a thermal trap if the building stores heat and the air blocks evaporation. The next frontier is precise prevention, combining apartment-level thermal models, humidity forecasts, health risk factors, passive cooling, and grid prioritization, fast enough to identify which homes will become medically dangerous 24 to 48 hours in advance. If you want first principles documentaries about the engineering constraints behind humanity's future, stay with CivilizationX. The constraint is real. The data exists. Whether the systems built around it can act on it at scale, that is the next engineering problem.